Here we present our ELL 100 assignment on FM radio receiver presented by Abhishek Yadav and Bharti Meena. Let's begin with the block diagram of an FM radio receiver. The FM radio receiver consists of an antenna which receives signals from various stations. The RF amplifier selects and amplifies the desired station from the menu. It is adjustable so that selection frequency can be altered. This process is called tuning. In cheaper receivers, the tuning is fixed and the tuning filter is wide enough to pass all signals in the FM band. The selected frequency is then applied to the mixer. The mixer and the oscillator form a frequency changer circuit. Mixer and the oscillator. The output from the mixer is the intermediate frequency, which is denoted by IF. The IF is a fixed frequency of 10.7 megahertz. That means no matter what the frequency of the selected radio station is, the IF is always 10.7 megahertz. The IF signal is fed to the IF amplifier. The advantage of the IF amplifier is that its frequency and bandwidth are fixed, no matter what the frequency of the incoming signal is. This makes the design and operation of the amplifier much simpler. The amplified IF signal is fed to the demodulator. This circuit covers the audio signal and discards the RF carrier. Some of the audio is fed back to the oscillator as an automatic frequency control voltage. This ensures that the oscillator frequency is stable in spite of temperature changes. The audio signal voltage is increased in amplitude by a voltage amplifier. The power level is increased sufficiently by the power amplifier and then driven by the loudspeaker. This is the process of an FM radio receiver.
Now let's come to the simple circuit diagram of an FM radio receiver. When it comes to making an FM receiver, it's always thought to be complex design. However, one transistor simple FM receiver circuit explained here simply shows that isn't the case after all. Here a single transistor acts as a receiver, demodulator, amplifier to constitute a wonderful tiny FM radio. It's basically based on a super regenerative audio receiver circuit, where the use of minimal components becomes the main feature of the unit. However, fewer components also means a few compromises involved. Here the receiver requires a large metal base for grounding the unwanted signals and for keeping the noise factor to the lowest. And also this system would work only in places where the reception is rather strong and thus may not be suitable in areas where the signal strength is thinner. As mentioned above, the circuit is basically a single transistor super regenerative RF oscillator with a constant amplitude. Here we have tried to enhance the design such that amplitude becomes considerably magnified in order to turn off the transistor completely during the oscillations. This is called for an increase in the feedback capacitor and also to use a transistor specifically designed for handling extreme high frequency ranges such as BF494. Further modifications include an inductor with the emitter of the transmitter and a capacitor across the emitter resistor of the transistor. Due to this transistor is switched on as soon as the base emitter voltage of the transistor falls significantly, resulting in an abrupt cut off in the oscillations. However, this prompts the emitter capacitor to discharge, allowing the collector current to yet again resume its flow, initializing a fresh cycle of oscillation. The above happening forces circuit to flip-flop between two situations, oscillator off and oscillator on, resulting a sawtooth frequency of about 50 kHz at the output. Each time the circuit flips across the above on off states results in a significant stepping up of the amplitude, which in turn constitutes greater amplification of the received signals. The procedure also gives rise to noise, but only as long as a station is not being detected. The above design has one drawback, though the output received from the above circuit would have greater content of sawtooth noise compared to the actual FM reception. A smart technique can be seen employed in the following single transistor FM radio circuit to the attribute better efficiency to this simple design. Here we pull out the emitter capacitor C5 ground link and connect it with the output. This results in a fall in the capacitor voltage as the capacitor current rises, which in turn forces the emitter voltage to rise, prompting the emitter capacitor to negate the situation at the output. This enforcement results in making the sawtooth effect on the received signal practically to zero, thus presenting an FM audio with much reduced background noise. Effectively, we have the channel through which the FM information is transmitted. Our radio picks up via the antenna all of that information. There is a mechanism through which we tune a filter that selects only the desired frequencies and all others are blocked. Amplification ensures and it derives our speakers. With regards to the frequency domain, all signals can be characterized by their frequency components. Just like time domain signals are characterized by their time characteristics, we simply exploit this by designing circuitry to block unwanted frequencies. A radio signal of 93.5 MHz would simply have a frequency domain characteristic of a single peak at 93.5 MHz. All this tells us is that all of the power is in that signal is contained at that frequency. Here, for example, is a 1 kHz signal represented in the frequency domain sampling the environment around us might yield something like this. Although the numbers are not likely to match up exactly since FM radio is transmitted at higher frequencies than those shown here. As we can see, there are several peaks representing power in the transmission channel. Our radio receives all of this information and filters out the unwanted data. This can happen either in digital space through software or in the analog space through electrical components. The implementation for each are quite different, but the overall goal is the same, filtration.
Here comes the culmination of our video. Thank you.